So I'd like to thank the organizers for inviting me for this fantastic event. Unfortunately, I will not be here tomorrow and I deeply regret. uh, but it looks like a very exciting opportunity. And, um, and I'd like to thank the organizers for giving me the opportunity to speak today. The topic I thought of describing is about the two important parameters that are often discussed and described in the context of microbiome. And there is some confusion in the way the papers are written. Sometimes they're not very clear what they're really studying. So I thought we'll spend some time about that. And today I basically will be going over some existing methods, and then I'll describe a method called ANCOM that we introduced a few years ago, and I want to clarify certain things just so that people understand why it works. And then I'll describe, when you have multiple groups, how do you compare the microbial compositions, and then I have some concluding remarks. And the nice thing is that I'm speaking to an audience who are very familiar with compositional data, and that's been a so that's really a pleasure, because a few years ago when we started describing microbial analysis, when we described compositions, we had tough time telling people that these are really compositional data. And so it's really a pleasure to talk to this audience who are quite familiar with this compositional. And the other thing is, a lot of people here are familiar with John Aitchison's methods for compositional data, so I'm really talking to or preaching the choir here anyway, so I don't have to really work hard to tell you why we should think of these as compositions. So what we really have is an ecosystem, and for example gut, and we take a specimen out of that, and the specimen is processed, and we get typically a data set looking like this, which we call as OTU tables. So we have m different OTUs, and there are n different subjects, and these are the observed frequencies. So that's the raw data that we come across. Then once you have a data like this, you're trying to make some comparisons. You're trying to describe subjects who are under one condition versus subjects under a different condition. You want to see how these taxa are different. And so the problem comes down to two important parameters as reflected in my title. So I like to go over these carefully. So there is something called abundance. So let us consider this ecosystem that consists of these five different taxa. So the green variety, there are about 10 of them, the yellow variety have 3 of them, and so on. So that's the ecosystem. And from such an ecosystem, you can construct relative abundances, which would be just abundance of each of these taxa out of the total. And of course, these are totally unobservable. You can never observe the abundance. This is something that you cannot know what it is. And relative abundances you don't get either. But these are theoretical parameters. So what you get is a sample from this ecosystem. So assuming that the sampling somehow is random. So what you have is, from this system you may have, so we call this as specimens now. So you got 2 of those yellow variety, 3 of those green variety, and so on. So that's the observed OTUs that you have, observed whatever terminology you want to use. And from these observed frequencies, you can construct the relative abundance in the specimen. So what you have is a situation where these are the observables below, and those are the unobservables. The abundance can never be observed. You don't know what it is, and so you cannot think of drawing any inference about the abundances just by looking at the observed abundances in the specimen or even the relative abundance. So it looks like. However, just looking at the relative abundances in the sample, if you got some sort of a random sampling going on, then you probably can say that, okay, these observed relative abundances are describing the true relative abundances in the population. So probably you can do some inference along those lines. However, there is a problem. While the relative abundances are rather natural to study, to describe the population relative abundance, consider the following. So let us say these are the taxa from a baby who was not exposed to antibiotics, and these are the taxa from a baby who was exposed to antibiotics. Nothing has changed between the two except that the green variety has decreased. Okay. So in terms of the change is really taking place in the green variety, but everything else is the same. If you compute the relative abundances, everything changes. So now if I were to draw comparisons between the two ecosystems using the relative abundances, I would conclude that the two babies are fundamentally different because all the relative abundances are different. While that is mathematically correct, that's a factual statement that these two groups have different relative abundances, you are not really understanding what is going on in the two populations. So what we would like to do is, can we infer, so we really are asking the following question. So looking at these relative abundances, can I say something about where the change has taken place? That's the question we are trying to answer. Given that we can never observe the abundances, we can never draw inference about the abundance from the observed abundance in the system. Okay. So point being, relative abundances, while they are very natural parameters to study, they do not tell the whole story, and they may not tell you the actual story that you want to hear. You want to figure out where the changes are taking place. So how can we do this? So before I go any further, there are three important features for this microbiome data. Again, I'm preaching the choir here, so I probably will just run through. Fundamentally, the library sizes are quite unequal in the samples because you can be having a very big range of library sizes. So that poses a challenge with these data. And people have come with various ways of handling that. For example, verification is commonly done, but you can do other things perhaps. Then the second important feature of these relative abundances is that they're non-negative and they sum to 1. So these are really compositional. So we will have three babies here, baby A, B, and C, and baby A has equal amounts or equal proportions of the three different bacteria in the other group. Baby B has none of the bifidobacterium but has 20 and 60 and 20% of the other three bacteria, and so on. So these are adding up to 100%, and they lie inside a simplex. Because these relative abundances lie inside the simplex, you cannot do any of the standard methods. You cannot do a t-test, you cannot do a Wilcox-Kruskel-Wallis test, you cannot do any of those kinds of tests. Mann-Whitney test, none of this are valid in this setting. Although you do see people using those kind of methods for these type of problems. So you cannot compare two groups just by looking at these kind of methods. And so often people don't recognize what is being tested. The third important characteristic, before I go further. So the common methods that are used for these relative abundances is to apply Dirichlet multinomial distribution. It's a very natural thing because you're looking at proportions, which you think of as a multinomial distribution, and because there will be variation between subjects, you put a Dirichlet prior on the parameters of the multinomial to capture the extra variation among subjects. So this Dirichlet multinomial type of distribution is used in some cases, and the parameter they really are testing there is the comparison of the relative abundances. Then there is literature coming from DSeq2. The DSeq2 method is used in this context, which actually original roots are in RNA-seq literature. And there, the comparisons are really in the expectation of the OTUs. And the null hypothesis, you think that they are testing the null hypothesis of equal abundances, but it's not quite right. There is an extra parameter there, and that makes the whole problem, the method, the way it is done, wrong. Then there is EDGE-R is another popular method that's used in this context, and there the test is really on relative abundances and using a Fisher's exact test and doing a permutation type test in that context. Then metagen-seq is another method that was introduced a few years ago, and that's again testing on the abundances, which controls for the library size in some sense. And then popular methods are variations of the ANOVA and Kruskal-Wallis test or t-test or any of those kind of family of tests, which some people use it for on the OTUs itself and some people use it on the relative proportions. So these are some of the variety of methods that are commonly used. They're all testing different parameters, and often it's not clear from the paper what null hypothesis they really are testing. And people just use this as black box and you get p-values and they report differences. And the one has to be careful what hypothesis you really are testing. So just quickly about Dirichlet multinomial, the reason one may not want to use Dirichlet multinomial, which looks like a natural model for these problems, is that the observed counts that you have, if you put a multinomial distribution, and I just said lambdas, you put a Dirichlet prior, what happens is that as a consequence of such modeling, every pair of taxa have to be negatively correlated. The observed correlations are all going to be negative because of the sum being bounded by 1. And it's a consequence of that. That makes no biological sense, because why should all these taxa be negatively correlated? It makes no sense. But it will force every pair to be negatively correlated. And in fact, if you go back to the paper that was published long back in 1962 by Mosiman in Biometrica, where he actually introduced this concept of Dirichlet multinomial as a model, as a probability model for independence, really. So if you want to discover independence, because the idea is underneath you have independent gamma random variables which generate this distribution. So the point being, the Dirichlet multinomial should not be used for this kind of, in this context, and so sometimes it is. The third important feature of these data is that you have lots of zeros in the data. The tables are filled with a lot of zeros. And there are a variety of methods available in the literature to deal with these zeros. Some add a constant delta to all the observed counts, and then some actually impute using some probability model, and some use zero inflated variations of data Gaussian model and so on. So there are a variety of methods available in the literature, and each of them have their own strengths and conveniences as well. But what we try to understand is, why do we see zeros? Can we try to understand the source of zeros? Can we try to break it down so that we can apply a suitable method for the type of zero you see? So the three types of zeros we consider are structural zeros. These are zeros you find because the taxa is not supposed to be present in a certain condition. So if you're comparing, let's say, rainforest samples with a desert sample, some taxa should not be present in the rainforest and some should not be present in the desert. So these are structural zeros. You will have them, okay? And you cannot impute them by any number. It makes no sense to impute these zeros. Then there are outlier zeros, which are basically, without your understanding of the sample you're working with, you may have sample mixed where there may be some structural heterogeneity in the data. You may have some samples, so you may be looking at a bunch of people and you're looking at, let's say, their samples from the lungs or whatever. So you may have some smokers in the mix, or you may have people without your knowledge may have had antibiotics in the sample. So they may induce some zeros in the data. So there could be some outliers in the data which could produce this. And the third would be the sampling zeros, which are probably likely a consequence of the library size. You didn't if it was not deep enough that you didn't observe some other rare taxa. So there are various reasons why you may have zeros. And we try to analyze and try to come up with some simple way of identifying these zeros in a given data set, because if data set you have, you don't know which of the three types of zeros you have. Again, this is a first shot at the problem, and there are better ways of solving the problem perhaps. So the way we handle the structural zeros is that for each taxon, we compute the one-sided confidence interval, and to see if the one-sided confidence interval falls below 0. And if it does, we declare that it will be it's potentially a structural zero, because sometimes you do see a non-zero element in the data when it should be 0. And in terms of identification of outlier zeros, really the data could be multimodal. You may not have a single mode in the observed data. And how do you identify the multi-mode? So you can have some zeros are because of, as I said, some outliers in the data. How do we detect these things? So we have a methodology which we developed a while ago for binarizing images, which becomes quite handy here. Here we are looking at the log ratios with respect to some baseline taxon, and we use a mixture of normal random variables for the log ratios, which is reasonable, and try to come up with the partition. So you may have something like this. So you may have the method separates out the groups conveniently like this. And if we are unable to sort either of the two, we consider them to be potentially zeros because of the sampling depth. And in this case, we impute all those data by adding a 1 to the data point. Okay. So the idea is once you are able to deal with these zeros, how do we now going back to the actual question, if I want to compare two groups, because comparing relative abundance is not always the best thing. It's okay, I mean, you can compare the relative abundance, except you don't know what is the source of the difference. If you want to compare abundance, how can you do that? Okay, that's the question we're trying to answer. It's not an easy question because you don't observe any data point that can estimate this unknown parameter. It's really an unknown quantity. It's impossible to do. So can we do something with the relative abundance to get to this question? That's what we're asking. And we are going to make some simple assumptions. So going back here again, the motivation was that I want to be able to detect this green variety from the observed data that I have. Using the relative abundance, I will not be able to identify the green variety alone. I'll be observing a whole bunch of other quantities. So we have a small lemma, but before we go there, I mean, again, I'm preaching the choir here. You work with the log ratios because we are working, relative abundances are all within 0 and are inside a simplex. You work with the log ratios to get out of the simplex to the Euclidean space, and this is the basic idea of HSN's compositional data analysis. So we work with log ratios as we go forward. So here is a simple lemma. Let me try to explain. So we have m different taxa now, I going from 1 to m. And let us suppose we are looking at two groups, group 1 and group 2, which are the upper indices for the and we are working with a log scale, and natural log mu I1 is the natural log of true abundance of the ith taxon in group 1, and natural log of mu I superscript 2 is the log of the abundance of the taxon I in the group 2, and the difference is some di. And so I'm taking a unit mass from the ecosystem, and that's the value of this. Okay? And d1, d2, dm are therefore just differences. So the assumption we are making is at least 2 are 0. In other words, not everything is changing between the two systems. The two ecosystems are not completely different. If they're completely different, the method that I'm proposing won't work. We should have at least 2 taxa that don't change in the abundance between the two systems. It's just a regularity condition that we need. Otherwise, we need to assume something and do something, not assuming anything and not doing anything is other alternate. So we make that assumption that at least 2 don't change. Just like in gene expression studies, not everything changes between the two conditions. That's the basic idea. If I make that assumption, then here is a simple lemma. So on the left-hand side here, natural log of mu j1 minus natural log of mu r1. So r is some other taxon. J is the taxon I'm interested in. Okay, I'm interested in taxon J, and R is another taxon. So I'm looking at the expectation of the log ratios of these two. Okay, in group 1. If that is different from the log ratio in group 2 for every taxon R, so that's the key thing here. For every R, these are different. So I'm working in the relative abundance world. If that happens, then I can infer that actually the abundances are also different for this particular taxon. It's a very simple result to verify, but it's a very useful result for this problem. It's just a simple algebra, it doesn't take too long to do it. So this becomes the basic idea behind ANCOM. So let me work with show you a toy example to illustrate what I'm saying. Okay. So consider these two ecosystems. On the top, I have ecosystem 1 and ecosystem 2. Those are the abundance table. In other words, this is the population. This population got 5 taxa, and the taxon 1 is same between, abundance of taxon 1 is same between the two. Abundance of taxon 2 is same between the two. Abundance of taxon 3 is same between the two. But taxon 4 has changed and taxon 5 has changed. Okay. Question I'm asking is, now I'm going to hide that. Let us assume that I don't see the table. Okay. I observe the relative abundances which are at the bottom. I'm trying to infer from this relative abundance table, I'm going to pick the 2 green varieties. That's my goal. And my lemma will let me do that. Is the problem making sense? So you can never observe those abundances, we never get to see those abundances. But if in a unit tissue, that's the distribution of the numbers, can I tell the green varieties are different just looking at this relative abundance table? Okay, so according to the method I just described, I need to compute relative abundances. So let's start with taxon 1. So I'm looking at log ratio of taxon 1 with respect to taxon 2, log ratio of taxon 1 with respect to taxon 3, with 4 and with 5, and I do it for both ecosystems. When I do that, what you see is that only 2 of those log ratios are different, the other 2 log ratios are not different. Okay? Now, if I do the same thing with taxon 2, so basically based on my lemma that I just described to you, I cannot infer taxon 1 is different between the 2 conditions. Okay? Because for me to declare taxon 1 is different, I need all the log ratios to be different between the 2 groups. So it's not, so I cannot conclude they are different. Same thing happens with taxon 2. I cannot, the log ratios are only differing in the last 2 groups, but they're not differing in the other groups. In other words, I cannot conclude that taxon 2 is different between the 2 groups. Taxon 3, again the same thing. Only 2 of those log ratios are different, not everything is different. But if I go to taxon 4, all the log ratios are different. Okay, so based on the lemma that I have, I conclude that taxon 4 has changed between the 2 conditions. Same way with taxon 5, I see that something has gone wrong. So again, taxon 5, again, you see that all 4 log ratios are different. So I conclude taxon 4 and 5 are different between the 2 conditions based on the lemma that I demonstrated. Okay? So that is, so it almost looks an impossible task to compare abundances of 2 groups when you don't have any kind of handle on the abundance data. But if you work with relative abundance and make the assumption that 2 of the groups are at least 2 taxa are not differing between the 2 groups, you can infer the differences. Of course, the problem here is that these are, the W is a random variable. For different samples, you'll get different, there'll be uncertainty associated with W because of the randomness in the data. So you need a statistical procedure here. Okay, so this is what theoretically should happen. So the way the ANCOM, because what I just demonstrated to you is a theoretical thing. It's not, because working with real data will have randomness, so there's a variability in the data and so on. So the W is really a random variable that we need to pay attention to. So the way it works is that first we deal with all the zeros the way I described to you. Once you have dealt with the zeros, for each taxon we perform m-1 test when you have got 2 groups, right? Because every taxon, I'm looking at the log ratio of that particular taxon to the other taxon. So there are m-1 taxa, so there are m-1 tests I'll be performing. Once I've done that, each test will give me a WI, and because I'm doing multiple testing here, I control using Benjamini-Hochberg procedure, but I agree, if you ask me, the Benjamini-Hochberg procedure is designed for independent p-values, and the p-values are not independent here, but however, I just go ahead and do it. That's what gene expression studies we just do all the time, but there are some positively and negatively correlated genes. But I'll just be an honest statistician and just do it. So So that's what we did, or you can do Bonferroni if you really are, if you don't like to do BH procedure, Bonferroni will be forgiving for the dependence. So anyway, so we come up with Wi is now a random variable for each taxon we get that. So we get a distribution of Wi's for the different taxa. Now we don't have an honest null distribution for Wi. That's a challenging problem. So what we did was we just derived empirically the distribution of Wi from the observed Wi's we have, and based on that we come up with a percentile, and we basically take the top 70% of Wi's to be significant. Okay. So that's the basic procedure, and once you have the procedure, then we studied the simulations. We did a variety of simulations in a variety of contexts. So I'm going to present to you one of the simulation studies. In fact, Sophie Weiss, I don't know if she's here, she conducted there she is. She conducted an enormous simulation study with a lot of different patterns and conditions. So I'm pulling out one of her data points. And remember, FDR is defined as expectation over all possible tests you're doing, right? It's an expectation over all possible random samples. So I'm providing you the mean values from her tables, but organized a little differently from her paper. So the setup that I'm describing, one example is, so we have 2,000 taxa taken from a paper, and there was a control group. We took a random sample out of that to describe the control group, and the treatment group was created by spiking a subset of those taxa at certain rates. So randomly spiked 5, 10, 15, or 20% of the taxa, and amount of spiking was 5 to 20%. Okay? And so that's the abundance table we have. And the variety of sample sizes were considered, 5, 20, and 100. And the number of simulations, so if you can correct me, is roughly 800. Is that right? About 800, yeah. And the FDR that we are trying to control for is 5% FDR. Okay? So when you do that, so I'm picking one example out of all that she did. And I admit to you, when the sample size is as small as 5, ANCOM will fall on its face. It's not designed for very small sample sizes. But if you have sample size of 20, it works reasonably well with the power and all. So here are the comparisons across the various methods. So this is the FDR, that is the expected number of false discoveries in the simulations, averaged over the 800 simulations. So the x-axis would be the different FDRs, y-axis are the different methods, and t-test based on just the abundance. You can see the type 1, the FDR you're making is roughly about 27%. In other words, in this simulation setup, 27% of all discoveries, if you just did a t-test, are false discoveries. You cannot believe them, that's what it means. If you compute the relative abundance and then do a t-test on that, that's really worse, because you are really now got a simplex and you're forcing a Euclidean space method on a simplex. And what you see now is the FDR jumps to about 40%. In other words, 40% on average of all your discoveries are really false. If you do metagen-seq2, you have the same kind of issue, about 12-13%, edge R about something around 12-13%, and D-seq2 about 25% errors. It's the false discoveries. And ANCOM controls the false discovery on average. Remember, this is on average. So if you go to Sophie's paper, actually she has given you the entire distribution, but this is the average of the distribution. That's how you define FDR by definition. Okay, so basically, none of these other methods control the false discovery rate in terms of the abundance, which is what you're trying to compare. Whereas ANCOM, it is designed for that, it captures that. It is well below the 5% level. But the question, of course, you can ask is that, well, is it going to lose power? Well, when the sample size is very small, it will not have a good power. But any sample size like 20 in this example, it compares very well with all these methods. The most important thing is the power comparison has no meaning if the false discovery rate is crazy. So these other methods have very high false discovery rate. So in other words, one probably should be careful using any of the other methods because you can't control the false discovery. Whereas the ANCOM does control the false discovery and gives you a pretty good power. So when you have more than 2, how much time do I have? 15? Okay. So when you have more than 2 groups, the problem gets very interesting and very exciting actually. So you're not comparing 2 groups anymore, you got multiple groups. So think of an answer variance. When you have more than 2 groups, you do ANOVA F test, and then once you do the F test, you start doing post hoc analysis and so on. You can do a variety of things actually. So the classical test, the so-called global test, which is what ANOVA would do, the null hypothesis says there is no difference between the groups for a given taxon. The alternative says that for a given taxon, at least one group is different. So it's a typical hypothesis of this kind. But this is really not a very useful, so I hate to say this, but ANOVA is really a nice test, but it's not practically useful test. It's not, why would you do an ANOVA going into, if you're a scientist, you come with some hypothesis that, hey, I got this new treatment, I want to see if it's doing better or worse. I don't want to test a hypothesis that is no different, unless you're doing some clinical trials where FDA requires you to be doing a two-sided hypothesis. So instead, what you really are interested in is directional tests. In other words, you want to know the null hypothesis, there's no difference among the groups. The alternative is that the mean expression has increased, or mean abundance has increased or decreased. You want to test hypotheses of that kind. But now the number of tests will climb up a lot, so we have developed methods to deal with this kind of thing. So I think since I don't have time, and I knew I won't have time, I'm just hitting the main types of problems that we are trying to work on. And then similarly, you could be interested in comparing against a control group, or you want to compare all these different experimental groups against a control group. So then you are testing a slightly different hypothesis. Now this is almost like a Dunnett type of test, but variation on that. So again, you can control for the false discovery rates suitably by modifying the ANCOM to deal with these things. And another test you typically are interested in is doing trend. You want to know, so let us say there are 4 groups of babies born vaginally and no antibiotic exposure within the first month. Babies vaginally born, but they're exposed to antibiotics within the first month. And the third group is they're C-section born, no antibiotics. And fourth group is C-section born and exposed to antibiotics. So clearly G4 and G1 are sort of two extreme groups. G4 group is probably the most affected group, and G1 is the least affected group from a natural process. And G2 and G3 are. So this is known as a loop order. So the null hypothesis of interest is basically there's no difference between the 4 groups. The alternative is that G1 is better than G2, better than G4, or G1 is better than G3, better than G4. So you can be testing hypotheses like that. So you can be testing for very targeted hypotheses, and we've been developing methods to deal with such specific hypotheses when you have multiple groups. Or you could be interested in testing for trends. So you have no detectable levels of toxin in the breast milk, and as the levels of toxin increases in the breast milk, does the composition of abundance of a taxon, does it increase or decrease, things like that. So again, we have developed methods of this kind of thing. So basically the problem reduces to rewriting the hypothesis into a testing against an alternative, which is the parameter of interest is inside a convex cone. And then we have been developing methods to deal with those kind of constraints. So I think I would like to stop here. So we have been developing software to deal with some of these questions. And the methodology allows for covariates, allows for repeated measurements, and all that kind of stuff. So I think I'll just provide one analysis of a study that with Meritas data, where we were looking at babies who are naturally born and C-section born who never received any antibiotics. So the first month, when you apply ANCOM, so what we discovered is in the first month, for day 4, the vaginally born babies are quite different from the C-section born babies in terms of those taxa, in terms of bacteroidetes, firmicutes, actinobacteria, and proteobacteria. And it's kind of obvious because bacteroidetes is typically not present for C-section born babies. And as you can see, the significance, the difference is quite significant. When you look at day 120 now, the babies born through C-section start to catch up with the vaginally born babies. You can see some bacteroides coming back and actinobacteria through breastfeeding and so on. And by the time you come to day 730, that is 2 years, all 3 groups, the 2 babies and the mother, they look very similar. There's no significant difference between the groups. So in conclusion, we are developing these methods to deal with abundance and not just the relative abundance between groups. And so the ANCOM method is available through an R code that we developed, and if anybody interested can contact me, or I think it's available in Chime too. Right. And we are coming up with an alternative to ANCOM, which really speeds up the whole process and gets around some of these issues of deriving the null distribution of WI. So with that, I'd like to thank my collaborators. Siddhartha started this process a while ago. Rob Knight, we worked with quite a bit, and Merita, who's data we analyzed and who was part of our research. Thank you very much.
Do we have any questions?
Yes.
How do you think this would compare, just putting on my crazy speculative hat here, how do you think this would compare to a stage-wise selection of CLR coordinates? So, where you use a stage-wise rejective procedure where at the first iteration you consider every CLR coordinate for the relative abundances, and then you either do a test, two-sample test, or a test with the trend or something like that. You find the one with the highest effect size, or the lowest p-value, and you have a p-value, if the p-value is below some stage-wise rejective family-wise error rate procedure like Holmes-style p-value cutoffs, you could see, okay, the first iteration you have 100 species, you have 100 CLR coordinates, you find out which one has the lowest p-values, that p-value is less than you would expect under some Bonferroni correction, and if so, then great, tick it off, look at the subcomposition of the remaining species, repeat the process of the CLR coordinate, now only comparing them with each other. Now you have 99, does the 99, the lowest p-value fall below the threshold of multiple comparisons for 99 species and so on. But mechanistically, how do you think yours compares to that?
So it's a great question, because we actually have a follow-up paper. We looked at the relative abundance to get away from this adjacent like log ratios, to look at CLR kind of thing, but little modification to that. So come up with some sort of a variation of a geometric mean, because we wanted to adjust for the library size as well. So we did that along the lines you're describing. It does do well, but the problem there is that you still have the issue of multiple testing. I mean, you can go back, and so you need to reconstruct the multiple testing in 2 layers. So you need to come up with first layer of alpha levels have to be corrected together. So yes, that's possible. And as I said, we have done that. It doesn't gain a lot of power in any way, and it doesn't FDR control. This is a better control than that one. So we have tried. So that was the paper that was published in Frontiers just recently.
Yeah, it'd be interesting to see if that sort of stage-wise selective procedure can get you similar, accurate Q values, or
yeah, you could.
The procedures for family-wise error rate corrections. If you can also, by doing this hierarchical process, get well-defined Q values and stuff like that.
Yeah, I totally agree with you. I think that's what we try to do, that it doesn't, so in terms of power, it doesn't gain a lot of power with this, so we just left, well, we didn't give up, but we published the paper along those lines. We also described trends in that paper, actually. Yes, please.
You start with the absolute table, the absolute abundances.
Yeah.
Hello? You start with the absolute abundance table, and then you use that to create a relative abundance table, and then use the elegant lemma to make inferences about the absolute abundances using the relative abundances.
Exactly.
What is the reason to not use the absolute abundances, I guess the read numbers, directly for comparison? I'm sure there is a good one. I just don't see it.
That's a great question, and I think that's what some of these other methods are trying to do. And the problem with that is the library. So think of this way: you got 2 forests, and you want to compare the number of animals of a certain kind between the 2 forests, except you don't know the sizes of those forests. And now you took a random sample of 2 sets of random samples. comparing these two samples alone doesn't tell you the whole thing about the population size. That's why you have to bring some of the relative abundance into the mix.
Okay.
And that's the reason why we did that. And some of these other methods, in fact, DSeq2 tries to do something along those lines. They look at the expected values of the observed OTUs with corrections to account to some extent about the population size, but they are not very effective.
Oh, some normalization. Okay.
Yeah.
Okay. I see. Thank you.
Thank you. I would like to know that if you are going to develop a regression version of ANCOM for the continuous data, so you have mentioned that you have do some multiple group comparison, right? So is there any like regression version?
Yeah, that's a great question. So we have a slightly, so I had to be careful. So when you say regression, you're really looking at the slopes of a regression parameter and how does that, how can we do inference? We haven't done that yet because that is getting.
Is it possible?
Well, exactly. So the new version that my student is developing, that's exactly where we are going.
Okay.
So the formulation, we modified it so that we can accommodate that, where ANCOM in its current formulation will not be convenient for continuous predictors.
Yeah,
in that sense. But we can adjust for continuous predictors, we can do that. But we can't infer about the continuous predictors the way you're thinking.
Okay. So the other question is that I'm just wondering if, how about the computation time of this tool? I mean, is it depend on the numbers of the features or a number of the groups you are going to compare? So if we are going to analyze functional metagenomic data, it will include, I mean, much more taxa or KOs than OTU we are going to, we have done in 16S data. So how about the computation time?
Yeah, that's a great question, and I think that's another reason why we are going in this direction.
Okay, thank you.
So as the limit, the thing that makes this computationally intensive is because the number of taxa, as it grows, the computation time grows. But the way I argue with biologists is that they spend years to collect the data, so I should be allowed to spend a few days to produce the analysis.
Okay, thank you.
Any more questions? Oh.
Hi, I had a question about the types of zeros and imputing sampling zeros.
Yeah.
So I was wondering how you can just assume them to be one. I mean, what if you had variation within the undersampled, or like would it just be better to leave them as zeros?
Yeah, so I think, as I said, this is really a first shot at the problem from our point of view. So we just took it as 1 because 0, the nearest integer that is non-zero is 1. So that was the only motivation. But there must be clever ways of doing it. In fact, Hongzhi Lee, he has got some really interesting methods to do that using, he regresses on the library size, which plays a big role in this. So you need a little more sophistication than the naive thing that I have done for that. But the idea is we try to partition the types of zeros, which is important, I think, rather than just imputing in every case. So that was the contribution here, but I totally agree with you. There are sophisticated ways of doing it, and we haven't done that. But Hongzhi has got some ideas.
All right, if there are no more questions, we'll start to move on to our next speaker.
Thank you very much.